All right, welcome back to AP Physics 2 training from National Math and Science Initiative. We're now on Module 5, which is Physical Optics. Physical Optics is not a lot, folks, so we only have an A and a B part here. My name's John Frensley. I teach at Prosper High School, Prosper, Texas. And so what's our focus? We're going to discuss the behavior of light when it's modeled as a wave. This behavior of light when it's modeled as a wave. Okay, so students need to know the relationship between wavelength, wave frequency, and wave speed. Please tell me you teach that in P1. Specifically the speed this time, because light will be the speed of light. They also need to be able to look at the graph of a wave and turn it into the equation for a wave by looking at the frequency or the wavelength on the graph. Let's see, they need to know about diffraction of light waves, interference of light waves, Doppler effect only qualitatively, single and double slit diffraction. We haven't seen any thin films yet. I'm just going to pray that we don't see any thin films. I hate thin films. I'm not going to go over it in this training. I just hate it. I like thin films. I think they're cool. I just don't like teaching them. I feel like it's a lot of trouble for just a little concept. It just doesn't work for me. Okay. I know what you're thinking. You see that number and you say 4%, only 4% of all the released points on the AP exam are physical optics? Oh, well, if you do a ratio, if you do like 30 weeks, 4% of 30 weeks is really just 1 week. But I have a warning for you. This is a serious warning. We recommend you take a little longer, maybe 2 weeks. Why? Because diffraction and interference topics have shown up a lot more for electron diffraction for quantum mechanics. What am I saying? 2 release-free responses have had diffraction and interference of waves, electron waves. Not light waves, but electron waves. I don't think you're going to do a good job of teaching electron wave diffraction unless you do a good job of teaching light wave diffraction and interference. So let's do a good job during this unit, and then that way we fight a battle that would be a big battle, make it a small battle in our quantum mechanics unit. Okay. Students do need to know when light can be modeled as a ray and when light can be modeled as a wave, and why. Why would we use a ray model? Why would we use a wave model? So we can deal with light. So first of all, light can always be modeled as a wave. All the time in classical physics. That means not quantum physics. So in classical physics, you know, when we're dealing with things that are geometries and things that are bigger than individual atoms, we can always model light as a wave, but that makes the math really tough. You can still find focal lengths. You can still find images, even with wave optics, but it's awful. So we're only going to model light as a wave when we have to. Light can only be modeled as a ray in very certain cases. When light's modeled as a ray, there's really no way we can talk about diffraction or interference. When light's modeled as a ray, we cannot say the light bends around a corner, diffraction, or it interferes when it's in or out of phase. Can't do that. So the only way for light to be modeled as a ray is if the light interacts with structures that are much larger than its wavelength. What kind of structures? Lenses that are far bigger than the wavelength, passing through holes or slits, much bigger than the wavelength. Imagine a window. When light travels through a window, you see the rectangular outline of the window on the floor, let's say if the sun is coming in. You don't see an interference pattern because the window is much bigger in size than the wavelength of the light coming through. However, if you have a little pinprick, it's very small, 1,000 nanometers maybe 10,000. Light comes through that, you'll see an interference pattern because that's on the order of the wavelength of light. Maybe 1,000 nanometers will do that. Light has very specific wave properties. Students need to know that the light travels at the speed of light in vacuum, that light is made up of 2 transverse waves. One's an electric field wave, one's a magnetic field wave, and that the electric and magnetic field waves are both perpendicular to each other and perpendicular to the direction of travel. So if, for example, this is the magnetic field wave, I don't know, B, is this B in sign language? And I'll do this for electric field wave. If this is the magnetic field wave and this is the electric field wave, they look like this and they travel perpendicular to the electric and magnetic fields. It's worth making sure they know that. We categorize light by its wavelength or frequency. Students do need to know from lowest to highest frequency, radio waves, microwaves, infrared. Visible light, ultraviolet, X-rays, and gamma rays. I feel like they need to know that order. Lowest to highest frequency. When waves encounter barriers, they diffract. Please show them that with a wave tray or something like that with water. That waves can diffract, turn corners around an obstacle. Classical matter cannot. So light must be a wave if it can diffract. Waves can interfere constructively and destructively. Classical matter cannot. That's going to bring you to your diffraction and interference experiments we're going to do in Part B. Waves passing through one or more slits form interference patterns. They need to know that. When waves change media, okay, this one is really important. When waves change from one medium to another, frequency stays the same. This is very important. When waves go from one medium to another, the frequency of the wave stays the same. But wavelength and speed of the wave both change. They're going to change in inverse proportion to the index of refraction. What do I mean? If you go from an n equals 1 to n equals 2, then the wavelength will be half as much. If you go from n equals 1 to n equals 3, the wave speed will be 1/3 as much, as an example. They need to know that. How do you over-represent 4% on an exam? I'm not even going to go through the naming convention seriously. We've had some slit diffraction, but it's been only multiple choice questions and one free response on single slit diffraction that was part of the practice exam that was published behind the audit wall and was never given as a true exam. We have a little bit of slit diffraction in the AP course description. It just shows up rarely. However, I would ask you to go over it with your students and maybe use some of these old Physics B free responses if you can find them, especially these two. These are some really good ones I feel like align best to AP Physics 2. Thin films. There was something that was like a thin films question. There's only been one. There was a thin films question back in Physics B. I don't even know if it's a battle worth fighting, honestly. Okay, treating light as a wave. Comparing sound to light. Taking a graph of a light wave and turning it into an equation for the light wave. Please look at these. These dealing with just wave ideas in general, you might be able to get some of those battles fought in Physics 1 so you don't have to fight them in Physics 2. That'd be nice. Hands-on, I have the students do activities where they're using diffraction concepts to measure the width of a human hair. I'll show you that in Module B, Part B. The distance between data tracks on a CD, I'll show you that in Part B. There is a lab, it's called the Finding the Wavelength of Red Light Lab. Calculating interference pattern angles or positions of maximums and minima. Drawing diagrams of interference patterns, that's important. How diffraction concepts can be used to measure small widths. It's a good class discussion to have. So, in summary, don't spend too long on it, obviously, but spend some time on it and use this as a way to bridge your students over to electrons diffracting and interfering. All right, I'll see you on the next one.